Theoretical cosmology suggests early universe models, like loop quantum bounces, might leave behind a pre-temporal information layer, a structural geometry that exists prior to classical time. The Cosmic Acoustic Topo probe proposes a method to detect this layer. It searches for a synchronized cross-modal resonance, a singular motif vibrating identically across vastly different physical mediums. Specifically, the protocol monitors 3 channels: astrophysical dust acoustics, measured in hertz, optical structures in the terahertz band, and slow bioelectrical voltage shifts, denoted as delta V, running through terrestrial forest networks. The catalyst that drives this simultaneous alignment is extreme space weather. When solar transients and coronal mass ejections sweep across the heliosphere, the resulting energetic wave acts as the trigger, proposing a direct observable link between an interplanetary plasma wave and a localized tree root system requires extraordinary proof. The protocol outlines an exact, airtight experimental design to test this connection. Historically, unconventional physics models search for static numerical constants to force a connection between disparate phenomena. This numerical cherry-picking guarantees false positives. Previous literature suggested a specific cross-model frequency ratio of 4.86 times 10 to the 15th power. This protocol explicitly rejects that number as a universal constant. Attempting to lock in a static ratio is an analytical trap. Instrumentation variance, background noise, and environmental drift naturally alter cross-modal readings across different missions and biomes. Instead, the probe calculates a dynamic ratio, denoted as R, dividing the terahertz frequency by the dust acoustic frequency. This ratio is estimated independently for every single solar event. The validity of the hypothesis rests on the mathematical behavior of this dynamic ratio over time. It must demonstrate inter-event stability within a strict tolerance and prove its out-of-sample predictive power. By abandoning fixed numerology, the protocol forces the hypothesis into the realm of strict operational falsifiability. The physical signature must replicate predictably, or the theory is discarded. The core data problem is that standard frequency and amplitude analysis cannot reliably link an interplanetary plasma wave to a bioelectric voltage shift. The signal geometries are entirely incompatible. To solve this, the protocol relies on Betty spectroscopy, an application of persistent homology that extracts the underlying shape of the data. The pipeline begins by taking a noisy, one-dimensional time series signal and applying a sliding window delay embedding across the data points. As the window moves, that linear data is projected out into a multi-dimensional point cloud, exposing the hidden geometry of the waveform. Next, the system calculates persistent homology by computing Vietoris's complexes. Translucent spheres expand simultaneously around every coordinate in the cloud until their edges intersect and connect. As the overlapping complexes fade, they reveal core structural motifs. The target signature is a Betty 1 feature, a persistent, closed topological loop hiding within the chaotic data. These extracted topological loops are then compared across the dust acoustic, terahertz, and bioelectric channels to calculate topological mutual information, or TMI. The operational threshold is aggressive. To register as a true cross-modal lock, the TMI must exceed 0.10 bits across multiple consecutive epochs, strictly controlled against false discovery rates. By extracting and comparing topological geometry, researchers can mathematically verify when 2 entirely distinct physical mediums are processing the exact same underlying information architecture. Securing this topological data requires a dual terrestrial and archival approach, allowing the protocol to launch immediately without waiting for a new dedicated deep space mission. Track A focuses on the archives. Researchers hunt for low-frequency dust acoustic modes ranging from 0.1 to 500 Hz inside decades of historical spaceflight data. The analysis reprocesses Cassini's ring plane passes and Voyager's interplanetary plasma wave intervals, scanning for structural anomalies. Track B operates concurrently on Earth. A 1-dunum forest array, wired with hundreds of low-power electrodes, measures bioelectric potential transients in the root system. This biological network is paired with an overhead clear-sky terahertz radiometer, providing continuous structural observation of the local atmosphere. Alignment relies on absolute timing. Both the Track A archives and the Track B live feeds are locked to precise GPS timestamps, corresponding to known historical and live coronal mass ejections. Track B introduces a critical vulnerability. Local environmental confounds, such as temperature spikes, can easily fake a biological voltage response to terahertz signals. The protocol implements strict mechanism-agnostic controls. First, IR micro-LEDs apply matched thermal heating to the test environment to rule out microthermal gradients as the true driver of the voltage shifts. Second, the array continually logs local magnetic field covariates. This ensures that extreme low-frequency Schumann resonances aren't the actual cause of the biological reaction. Physically isolating the archival space data from the live terrestrial biology is essential. It eliminates local environmental bias and ensures the resulting topological comparison is entirely blind. Testing the full cross-modal theory on Earth faces a hard limit. The tropospheric turbulence and complex biological background noise make it impossible to prove direct, isolated terahertz-to-dust coupling. Track C proposes an optional specialized CubeSat relay situated at the lunar terminator to bypass this interference. The stark day-to-night thermal contrast on the lunar surface naturally generates a lopsided, self-maintaining dust cloud along the terminator line. This provides an ideal, massive, airless laboratory. Orbiting directly through this dust field, the CubeSat emits a specific, tagged terahertz envelope straight into the particulate concentration. This graph displays the demodulated spectrum recorded by the onboard UVS and LiDAR arrays. A flat noise floor is punctured by a singular, sharp vertical spike. That spike indicates a narrow band return precisely at the tagged frequency, requiring a quality factor of at least 1,000. The primary engineering risk is the CubeSat's own internal electromagnetic interference, creating a false positive feedback loop. To safeguard against this, the transmitter applies randomized delay jitter to the signal. If the dust backscatter precisely matches the randomized jitter, the physical coupling is real. If it fails to track the jitter, it's internal EMI. Operating in a true vacuum strips away Earth's complex variables, isolating the exact physical mechanism needed to prove or disprove the terahertz dust resonance. The scientific value of the cosmic acoustic Topo probe lies in its strict failure criteria. The theory is designed to be systematically and cleanly killed by the data. The absolute first operational gate is P0 bench first. No space or field operations begin until the lab work succeeds. P0 requires researchers to achieve a signal-to-noise ratio of 3 or greater inside a microvacuum, using iron-doped grains under controlled magnetic drive conditions. During tracking, the failure condition is purely mathematical. If the dynamic ratio R varies by more than a factor of 2 between different solar events, the hypothesis is immediately rejected. The predictive models are equally unforgiving. The out-of-sample data must yield an area under the curve greater than 0.7. Any lower, and the topological model is deemed useless. If any single hard-coded gate is failed across the protocol, the cosmological claims are permanently terminated. No excuses, no moving the goalposts. Even if the grand pre-temporal hypothesis fails these rigorous tests, the infrastructure does not go to waste. The protocol leaves behind a highly functional cross-modal anomaly detection pipeline, advancing classical space weather prediction and bioelectric monitoring at minimal cost.